Welcome to Mastering Solutions. In this general problem, they ask us, does a real automobile have constant acceleration? They give us information for this Porsche 944 Turbo, and they tell us that the maximum acceleration is shown in the table down here. For part A, they want us to convert the velocity from miles per hour to meters per second, and then they ask us to make a graph of the velocity versus the time. Based on our graph, they say, is the acceleration constant? And they want us to explain that. So first, let's start off and convert all of these miles per hour to meters per second. To do that, we're going to have miles on the top divided by hour. So this is another representation. You've probably all seen this, miles per hour. This is the same thing as down here. So now what we want to do is we want to do dimensional analysis and convert these units to what we want. We want the units to be the same on the opposite so that they'll cancel, giving us the units that we want. So on the bottom, we know that we'll have miles down here, and we want to put that into meters. We know from the useful data table at the beginning of the book that there is 1609 meters in 1 mile, and then the miles will cancel, and now we're left with meters on the top, and we need seconds on the bottom. So I'll leave this blank, and then we'll just substitute in the numbers here for each of them. So then over here, we want hours on the top so that the hours will cancel appropriately, and we want seconds on the bottom. So in 1 hour, there is 3,600 seconds. And again, that was taken from the useful data section. These two units right here are extremely useful for the test, so I'd probably memorize these two. Most of the other ones you can, in kinematics at least, you can reason out by going from miles to feet to centimeters and etc. These ones just will save you quite a bit of time. So now we have meters on the top and seconds on the bottom. So what we'll be doing is taking the number and then we'll multiply it by 1609 since 1609 is on the top. And then we'll take that and divide it by 3,600, which will give us meters per second. So for the first one, we have 41 times 1609 divided by 3,600 gives us 18.3. So let's put another section right here. So we have 0 and then 18.3 there. Now we have 66. And let's do this. Let's plug this in here, and then we'll go to the beginning and we'll change that to 66. Gives us 29.5. So 29.5 meters per second. We'll do the same thing with 83. 83 gives us 37.1. We'll round that up. 37.1. For 97, we have 43.4. And last one, 110, gives us 49.2. So here are all the velocities converted from miles per hour to meters per second. And now they ask us to make a velocity versus a time graph and to see if the acceleration is constant from that. All right, so here's our graph with all of the data points plotted for velocity versus a time graph. And we have it in meters per second versus seconds. So you can see from the line here, if we had a constant acceleration, that would mean that the slope of the line would be the same, or the same line. It wouldn't have any sort of a curve to it. But you can see here the slope is changing. It's getting slowly flatter and flatter as we go along. And so in answer to the question here for part A, is the acceleration constant? No, it's not. It's changing, and we can see that because the graph's slope, as we said, is not a straight line. For part B, they ask us to estimate how far the car traveled in the first 10 seconds. And in this, what we're going to do is to get the area underneath the curve down here. Since it's not a straight line, we have to, as we talked about, estimate. So I don't usually like it when they put these into the problems because estimating could give different values for everybody. So look at your own graph and do your best estimate. Because we're trying to get the area underneath the curve, you can see how we kind of have a triangle shape here. And so to get the area of a triangle, it's 1/2 times the base times the height. So to estimate this, let's get the base of the triangle, which is 10 seconds. So we'll have 1/2 times the base, which is 10 seconds, and times the height, we're going to have as 49.2 meters per second. So 0.5 times 10 times 49.2 as an estimate of the area underneath the curve is 246. So we could round that to 250. But if you notice, like when we draw this, it's not a true triangle. There's kind of this area above it where it kind of bows up and goes down. And so what we're going to do is we'll actually estimate higher. So I'm going to estimate larger at, again, this is just, everybody's will be slightly different. I'm estimating at 270. Lastly, for part C, they tell us that if we draw a smooth curve through the points on your graph, use the estimate of the car's acceleration at 2 and 8 seconds and to put the units into SI units. So again, as they're talking about here, remember that acceleration is the slope of the velocity graph. So we need to estimate what the acceleration is at 2 seconds. So right here, and 8 seconds right here. The formula for acceleration, of course, is the change in the velocity over the change in the time. And the change of anything, as we've discussed in many of the videos, is final minus initial, t final minus t initial. And so what we'll do, you could draw a tangent line and get the slope of that line, but what I'll be doing is taking the average between the 2 points around it. So since it's just an estimate, if we take the acceleration from 0 to 4, that average we can say is a good guess. And then the acceleration from 6 to 10 is also a good average for that one. So for 2 seconds, so the final velocity at 4 seconds is going to be 29.5. And the initial velocity, of course, is 0 meters per second. We'll divide that by 4 seconds minus 0 seconds. So that will give us, of course, 29.5 meters per second divided by 4 seconds. So 29.5 divided by 4 is 7.3, so 7.4 meters per second. 7.4 meters per second squared, so that's the acceleration. So that is a really good estimate for the acceleration at 2 seconds. Now we'll do the same thing for 8 seconds. So we'll take the final at 10 seconds of 49.2 meters per second minus 6, which is 37.1 meters per second. And then we'll divide that by 10 seconds minus 6 seconds. So that's going to be 4 seconds on the bottom and on the top. So we have 49.2 minus 37.1. And we'll divide that by 10 minus 6, which of course is 4. So we have an estimate of 3 meters per second squared for that acceleration. So here are all the answers for the problem, the estimates of the acceleration, the graph, and how far the estimate it went, which will be, of course, in meters, since we got the area underneath the curve.